Hi, hello everyone. Welcome back to my YouTube channel Sporifii Learn. Today, let's discuss the chemistry chapter 1 of second PUC, that is the solid state. Let's see on what are the concepts that are covering in this chapter. Solid. Let's define solid. What is the meaning of solid? If you take the states of matter, right, we have as three divisions in that, right? Solid, liquid and gaseous state. If it is solid, it is tightly packed. That means no more gaps will be there between those particles. If you take liquid, it is free than this, if you take grass, this is very freer than all the three if you compare. Okay, now let's see on, if you take the solid, as we know that it will be states of matter constituting particles are arranged very closely. As I said, it will be arranged very closely, no more gaps will be also there. The constituting particles, it can be atoms, molecules or ions. It can be either atoms, molecules or ions. Let's see the properties of solids. They have definite mass, volume and shape. If you take a square and if you have arranged some particles in it, they have a definite square shape, right? So you can say it has definite shape and it is in some particular volume. That means it is occupying some particular vessel, or if you take some example, it is occupying some particular volume, and it has definite mass. Okay, they are incompressible and rigid. Okay, what is the meaning of incompressible? Means compressible means compressing means you can uh, like you can if you have two solids, if you take these both, you cannot compress this both, like uh, press or something like that. It will not change any of its state. It will not be pressed also, because it is solid. It is having very more mass and all. And rigid, let's see what is the rigid is nothing but it is very like what to say means very unbending or something, like it is very tightly packed. As we saw, it is tightly packed, so that is called as rigid shape. And intermolecular distance are very short and intermolecular forces are strong. See, if you compare this solids, right, see, these solids are nothing but crystalline and this is amorphous. Let's see on that. See, intermolecular distances, see, this distance between this and all are short. It is short, so you say this is short. And hence intramolecular, that force will be strong. Distance is short, right? Distance is short, so force will be high. Next, their constituent particles have fixed position and can only oscillate about their mean positions. Next, if we come on to the classification, this is based on arrangement of constituent particles. Next is, first one is crystalline solids. Crystalline solids are nothing but they are regularly orderly arrangement, that is iron, copper, diamond, graphite and all. See, what is the meaning of crystalline? Means they are arranged in regularly order. See, it is having some particular order. If you come here, this is having this like a similar to hexagon shape. This is having a similar to hexagon, 1 2 3 4 5 6, yeah, hexagon shape. And next, if you come, if you see from here also, it is having the hexagon shape, right? If you see from here also, if you come, it is having a hexagon shape. If you come from here also, it is having some hexagon shape. Here also, if you see, same. And here also it is the same. So you call this as a crystalline solids. Okay, if you come to the amorphous, that can have any irregular arrangement. Okay, as the name itself suggests, irregular means it should not have, see, the previous we saw was similar to something like this. Okay, here it was like this. Okay, but here it may be like this, it may be like this, it may be here like this, something, some irregular arrangements can be there in amorphous. Okay, that is the major difference between amorphous and crystalline. And here if you see the example, glass, plastic, rubber, they are having some irregular shape. Some plastic can have this like structure. Here it may have hexagon, or here it may have something shape like this. Here it may have something shape like this. Here you may have some hexagon shape. So it is having very irregular shape, that is called as what? Amorphous. And crystalline will have very regular shape. Okay, now let's see on to the properties. Properties, they have a definite characteristics, geometrical shape, they have a long range order, sharp melting point, they are anisotrophic, that is their physical properties show different values when measured along the different directions in the same crystal. They have a definite and characteristic heat of fusion. They are called true solids. Okay, they are called what? True solids, that is crystalline solids. And next, if you come as, they have a smooth, okay, smooth plane surfaces. Okay, see, this is the structure of amorphous nature of crystalline solids. Next, polymorphic forms of polymorphs. See, they are the different crystalline. Poly, the name itself suggests many, right? It forms a substance that are known as polymorphs, or this is also called as polymorphic forms. That is example, graphite and diamond. They have a irregular shape. Amorphous, right? Amorphous properties, if you come, they have irregular shape, short range order. Gradually it will melt or soften over a range of temperature. It should have some particular temperature in degrees Celsius or Kelvin, whatever it is required for that particular nature. And they are anisotrophic, isotrophic. The previous which we saw was anisotrophic, right? Here it is isotrophic. And when you cut sharp edge tool, they cut into two pieces with regular surfaces. They do not have definite heat of fusion. They are called pseudo solids or supercooled solids. Pseudo is nothing but you can say as false or something like that, and this is because they have a low tendency to flow through very slowly. Okay, now let's see the types of crystalline solids. There are molecular, the constant particles here is molecules. Okay, type, here T is missed out. Okay, type of solid is, there are three: non-polar, polar and hydrogen. Okay, molecules is the constituent particles. Next, they are having hydrogen, here hydrogen bonding, attractive force. Okay, bonding, it should be bonding. Okay, sorry for this, bonding. And it is having London forces, and this have hydrogen bonding, and this have peptide bond. Okay, peptide bond. Okay, this is electrical conductivity. Electrical is insulator. Physical, okay, physical nature is soft and hard. Melting point, okay, this is melting point. Low, very low, low and low. An example is chromium, Cl4H2, that is hydrogen, I means iodine, CO2 means carbon dioxide, HCl means hydrogen chloride, SO solid, NH3 means ammonia, H2O means water. Okay, ionic solids. Ionic solids, constituent particles is ions. Here it was molecular solids, it was molecules. Ionic solids, it is ions. Okay, bonding or attractive forces. Here it is Coulombic or electrostatic. It is either Coulombic or electrostatic. And electrical conductivity means it is insulators in solid, but the conducts in molten state and in aqueous state solution also. Physical nature, if you come, hard but brittle. Hard, it is hard. What ionic solids, the type of amorphous solids is hard in physical nature, and but they are brittle. That means they are something like easier, they are easier, okay, than other. The melting point is high, and CaF2, ZNS, MgO and NaCl, sodium chloride, magnesium oxide and zinc sulfate. They are the examples. E means calcium, F means fluorine, as you all know. Next is metallic solids. If you come to the constituent particles, that is positive ions. Okay. Bonding or attractive forces, that means metallic bonding. They have electrical conductivity, means they are conductors in solid as well as in molten state. They are hard but malleable and ductile. Okay. They are malleable and ductile. They are malleable means that have something like property it can be rolled without breaking into thin sheets or something like that. And they are ductile also. Melting point is fairly high. Examples, if you come, Fe, that is iron, uh, Cu, Ag, magnesium, Ag, that is silver, and Cu, that is copper. And covalent or network solids, the particles is atom. This is covalent bonding. Covalent bond, this has, if you consider this as one bond and this as two bond, the between them they have a covalent bond. And electrical conductivity are their conductors. Physical nature is hard but malleable and ductile. Same. Melting point is fairly high. And next is silicon oxide, silicon carbonate, carbon, that is diamond, and graphite. Okay. Next is crystal lattice. This is one of the most important concept that you have to understand here. That means, see, they are a regular ordered arrangement of constituent particles in 3 dimension. Okay, 3. A cube, if you consider a cube. 3D is nothing but they are visualized. See, they are nothing but 3D. Okay. See, they are 3D. Okay, this is a what? As you all know, it is a cube. This is called a 3D. Okay, it is 3D. So that arrangements are called as, regular ordered arrangements are called as crystal lattice. Okay, they are having points. Okay, the fixed positions on which the constituent particles are present are called lattice points or lattice sites, it also called as. They have, when repeated over again and again in 3 dimension, they give a complete crystal lattice. See, as you can observe here, they are repeated, right? Here is one cube. Let's see on. See, here is one cube. Okay, and here if you see, the another cube is there, the same. Okay, and here if you see again, here is one cube, and here is another cube again. Here also another. The same way, there are more than 3 cubes that will form a complete crystal lattice. Okay, unit cell, it is defined as smallest repeating unit. The which is most smallest repeating unit is called as unit cell. Parameters that we have to consider is dimension of the unit cell. 3 edges will be there. No, these edges may or may not be mutually perpendicular. Perpendicular is nothing but they have to be like this, right? They need not to be mutually perpendicular to each other. Inclination of the edges to each other, this denoted by angle alpha, beta, and respectively. Alpha is the angle between edges B and C, beta is the angle between A and C, and gamma is the angle between A and B. Gamma. Okay. Next, if you come, there are 7 crystal lattice, that is cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, and triclinic. Okay, this is the formula you have to remember, very important. This is alpha is equal to beta is equal to 90 degree in cube, and A is equal to B is equal to C. This also 90 degree, A is equal to B is equal to this, you have to remember as not equal to C. And the same way you have to study this all 7. Next, if you come for types of this, they have primitive and centered unit cells. They are having constituent particles at only its corners. Okay, but there are more one or more constituent particles and are present in addition to those present at the corners. Okay, they are present addition to those which are present, like it is addition to primitive. Types of centered is FCC. We call this as FCC. It constitutes one particle at the center of each face in addition to those particle at the corners. Body centered, this we call as BCC. Okay, and this we call as end centered cell, ACC. And the same way, you like next, if we go on, number of particles at different lattice position. Corner is nothing but, see here you can see this is one corner. If an atom is present at any one corner, it is shared by 8 unit cells. So only 1/8 of it is belonging to 1 unit cell. The what they are trying to say is, see, if you consider this as a center, that is corner. Okay, they are shared by 1, 2, 3, 4, right? Now that 4 in a cube, if you consider any corner, they are shared by 8 of any atom, so they are called as corner particles. Face centered, if you consider a face, that is, this is a, see, if you consider a cube, you have like this, right? Up here you have, let's use different color. Here if you see, this is called as face. Okay, that are present on the face, that is shared by 2 unit cells that have 1, and down also 1 face will be there, right? So two faces will be there. Okay, next is body centered. Body centered is nothing but it is not shared by any other cell, so that is completely belongs to the same unit cell. End centered is nothing but, if an atom is present, it is shared by 4 unit cells and the fourth belong to this unit cell. If you have primitive, it have 1 atom. If you have face centered, 3 atom. Body centered, this you have to remember. Primitive means it is 1, face centered means it is 3, and body centered means it is 2. Coordination number, it is the number of nearest neighbor of the particles. See, if you consider a cube again, and if you have to find the coordination of number of this, you have to see all the nearest neighbor. This is one nearest neighbor and this is another nearest neighbor. The number of all the nearest neighbors you should see in order to get the coordination number. If we see the close packed structure, in one dimension it is in contact with 2 of its neighbors. See, if you take this, it is in contact with this also and this also. So it is contact with 2 neighbors. In 2 dimension if you take, they can have in 2 ways. That is, you can have either square or hexagonal, right? Hexagonal. These are the 2 that will have in 2 dimension. And if you come in 3 dimension, they can have square and this hexagonal. See, here it was close packing, here it is close packed layers. The layers are there, so that are called as in 3 dimension. If you see for 2 dimension, see, they are having, see, if you see the example they have only marked here. If you see this, the square they have considered here. If you see, what they are trying to say is, the sphere of the second row are placed exactly above this 2 first row. This way the spheres are aligned horizontally as well as vertically. The range A is the coordination number is 4. See, 1 nearest neighbor, 1, 2, 3 and 4. So 4 is the coordination number of this square close packing. If you see hexagonal close packing, see, here it is 1, 2, 3, 4, 5 and 6. 6 should be the coordination number. Let's see. Yeah, see, 6 is the coordination number and it is AB type. The arrangement is AB type and they fit into it. If you see 3 dimensional, see, you can see this is a cube. As you can observe, you can see as the shape itself suggests, it is a cube, right? If you see, if you consider a cube in this, it has a simple cubic lattice. It is of type AAA. Okay, And this is a cube example that can be taken for 3-dimensional. If you take for close packing from 2-dimensional hexagonal close pack layers, means it is having placing over the first layer as well as third layer. If you place over the first layer, it is a 2-dimensional layer is considered as A, okay, and the second layer which is placed above the first layer is such a way they are present of the second layer and are placed in depression of the first layer. This gives type of voids. Type of voids is nothing but something gaps, or you can say in other words, that is tetrahedral and octahedral. And if you see the two possibilities for third layer, tetrahedral and octahedral. Octa means 8, okay. Next, if you see next concept, that is packing efficiency. It is one of the most important and repeated. You can mark as very important question, fixed question. This is, you can mark for a star. One of the most important derivation from will be there from this concept. If you see packing efficiency formula, let's define it. It is the percentage, okay, remember the word percentage of total space occupied by the constituent particles, okay. They are saying as total space. Total space is nothing but volume divided by the total volume of unit cell. Unit cell means it is single cell, right? Volume occupied by the spheres divided by total volume of unit cells into 100. Why? Because it is percentage. This is the formula need to calculate for packing efficiency. And if you see for FCC it is 74, BCC it is 68, simple cube it is 52.4. This derivation is very important. Derivation is very needed, and if you want this derivation, you can let me know in the comment box. I will try to do it in the next video by writing all the each and every steps. Next is radius ratio in octahedral. Radius ratio is nothing but r divided by r. See, its radius should be 0.41 times of the radius of the sphere. Octahedral void should be the, like, if you want the ratio between octahedral and the sphere, it is r is equal to 414 into r. So 0.414 can be written as r divided by r. So that is how you have the ratio. For tetrahedral void it is 0.225. And if you come for the density, if you have this simple cube, it is A is equal to 2r, and this A is equal to 2 root 2r, and BCC it is 4r by root 3, okay. Volume, if you come, 2r whole cube, 2 root 2r whole cube, or 4r by root 3. That means what the relationship or area, edge length you are having, that cube if you do, you will get the volume. Number of cell, that is simple cube, if you have one, body centered means that is BCC, it is 2, FCC means it is 4, cube means it is 1, okay. Next is crystal effects, that is you have types of effect is point effect, line effect. Point effects are nothing but they are irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance, okay. In a crystalline substance, as we all saw in the types of solids, the crystalline, they are very orderly arranged, right? So that is nothing but, if you find that, it is point defect. Line defect are nothing but they are from row of lattice, okay. If you see point, again if you divide this point defect, you have three types, that is stoichiometric or intrinsic or thermodynamic, you can call either any one of this, and non-stoichiometric, stoichiometric or non-stoichiometric, and impurity. Let's see, stoichiometric nothing but they do not disturb the stoichiometry of the solid, okay. Non-stoichiometric, they disturb, okay. And impurity means they are the due to presence of impurities. Impurities will be present in the cell or something like solid, okay. Next type is types of stoichiometric defect for non-ionic solid is vacancy. Vacancy is nothing but there will be having some particular gaps in that. That is called as vacancy defect. Interstitial defect means they have, when you consider a particular constituent particles, they occupy a interstitial site. That means this result in increasing in density of a substance. If you have some crystal over you, and if you add some in some particular substances or particles, if you occupy the interstitial site means it is called as interstitial defect. And if you come for, that was for non-ionic solids, right? As we also, it is for non-ionic solids. If you come for ionic solids, they have two, that is Schottky and Frenkel. Okay, Frenkel is also called as dislocation. Schottky defect is nothing but in this effect, equal number of cations and anions are missing. Equal number, you should remember the word equal number. It is basically a vacancy defect. It is basically a vacancy defect and decreases density. Let's see what is density. Density is decreased in Schottky, and it is shown by ionic substances, as we all know from the, it is for ionic substances, it is not for non-ionic, which the cation anion are almost similar sizes. It includes sodium chloride, potassium chloride, cesium chloride, and AgBr. Okay, AgBr. Next is, if you see the image, next, see here you are having negative, plus, negative, and here is something as left space, minus, plus, minus, plus. If you see the whole diagram, the number of cations and anions that are missing will be same. Okay, if you count all the positive ions that are cations, positive are called as cations, negative are called as anions. If you count all that, if you can see the number of missing all the cations and anions will be same number it will be having. In this Frenkel effect, it will be different. Okay, it is having from interstitial site, and this is also vacancy defect, and this is shown by ionic substance AgCl, AgBr, AgI, that is iodide. And next, if you see here, it is the same effect. It does not change the density, no change in the density. It will occupy the interstitial site. If you see type of non-stoichiometric, it is metal axis. This type of defect is due to excess of metal cations. Metal cation means positive ions. Okay, there will be missing of cations. That is, if you see this diagram, there will be missing of this. Metal deficiency means this is due to metal ions missing, like there will be missing of metal ions from the lattice. And next reason for this is anionic vacancy. If you see that cations are missing, that means anionic vacancy, right? Then presence of extra cations. And if you see the classification of solids based on electrical conductivity means conductor, insulators, and semiconductor. Conductors are ranging between 10 power 4 to 10 power 7 per ohm per meter are called conductors. Insulators are 10 power minus 20 to 10 power minus 10 per ohm per meter. Next, the same way, minus 6 to plus 4 per ohm per meter. Next important concept is band theory. A metal is characterized by a band structure. The highest filled band is called valence band, and the lowest unoccupied band is called as conduction band. Lower is called conduction, and next highest is called as valence. The gap between them both is called as forbidden band. Okay, see, well, let's understand. In case of conductors, the valence band and conduction band overlap. Okay, see, this is one example for conductors. See the partially filled energy, that is conduction band, and here also it is valence band. So they both are overlapping bands. Okay, see, they both are overlapping here. So that are called as in case of conductors. If you come in case of insulators, insulators. The forbidden gap is very high. See, forbidden gap is high, very large, and electron are unable to excite. If you come in case of semiconductor means small energy. That means here the forbidden state gap will be less. Types of semiconductors, if you come, there are majorly two types, intrinsic and extrinsic. Intrinsic are nothing but forbidden gap will be small, okay. Next, only some electrons may jump or may not be jump, and some show conductivity. Silicon and germanium are example. Silicon we call germanium as G and silicon as Si. These are the elements that you have to remember very carefully. Extrinsic semiconductors are, they are added semiconductors, it is called as extrinsic. That is, impurity is added and their electrical conductivity is high. If you come to the doping concept, the process of adding an appropriate amount of suitable impurity. Suitable impurity means to increase the conductivity of semiconductor is called as doping. Here also there are two types, N and P type. The name itself suggests N means negative, P means positive. These electrons occur like for group 15 elements. This is for group 13, positively charged and negatively charged. And diode, it is a combination of N type and P type. It is used as a rectifier. Transistors are nothing but they are made by sandwiching a layer of one type of semiconductor between two layers of the other type of semiconductor. The NPN and PNP type of transistor used to detect or amplify radio or audio signals. The 12 to 16 compounds are called as like group 12 and group 16 are called as compounds, and 13 to 15 are this gallium, arsenic and all. Next, every substance has some magnetic properties associated with it. Then they behave like magnet. And classification of substances means, this is very important concept to understand. Paramagnetic, diamagnetic, ferromagnetic, antiferro and ferrimagnetic. They are weakly attracted, they are weakly repelled. They are attracted very strongly by a magnetic field. They have an equal number of parallel and antiparallel magnetic system or dipoles. They have unequal number of parallel and antiparallel magnetic dipoles. This is the whole chapter of solid state. The three derivations I will upload in different videos. And thank you for watching the full video. Please make sure to like, share, comment and subscribe to my YouTube channel, and please do share with your friends also. Thank you for watching. Stay tuned for the next video.